Hello, my name is Jeffrey, and this is my video lab report for Physics 2211M, lab number 4. To introduce this lab, let's first analyze its purpose, its models and fundamental principles, and the main result. The purpose of this lab is to examine motion and energy of an oscillating spring system moving in 2 dimensions, and to apply the energy principle and the momentum principle. Because this lab is all about motion and energy, the two main physics principles involved are the energy principle, delta E system equals work done by surroundings, and the momentum principle, F net equals ma equals m delta v over delta t equals delta p over delta t. For this lab, it is assumed that the only energies acting on the system are kinetic energy, gravitational potential energy, and spring potential energy. And to obey the law of conservation of energy, delta K translational plus delta U grav plus delta U spring equals 0. Furthermore, the forces exerted on the mass can be modeled using a free body diagram. In this case, the spring force and the gravitational force are the only two forces acting on the system, and act in opposite directions to one another. As for the main results, the operational data and the computational model were very similar. The energy principle held true as the change in total energy was 0, and the periods of oscillation from x values were not the same as that from the y values. For the observational data, the system is the mass, spring, and Earth, and nothing is in the surroundings. This is done to make work done by the surroundings equal to 0. Initially, the spring is anchored at the origin, and the spring is stretched to 0.7 meters. Additionally, it is assumed that there is no work done on the system by letting go of the block, that there is no movement in the z-axis, and that there are no other energies acting upon the system aside from the ones listed. To extract the x and y position of the mass at each time step, I used Tracker and manually placed tracking points on the center of mass, then converted the lists into an Excel sheet and a CSV file. In the computational model, the first modified lines define the block's mass, its initial position, and its initial velocity. Delta t is also assigned to be 1/2 of a second. Next, the gravitational constant, the spring constant, and the relaxed length of the spring are assigned the proper values. L, L hat, and S are defined as well. Finally, the initial kinetic energy, gravitational potential energy, spring potential energy, and total energy are all defined. In the calculation loop, the previous energies are reassigned as initial values. F grav and F spring are defined as well and summed together to yield F net. The block's velocity and position are updated using the velocity update and position update formulas, and the values L, L hat, and S are updated as well. The new energy values are calculated and subtracted by the initial energy values to yield delta K, delta U grav, delta U spring, and delta E. The graphs for change in energy, x position over time, and y position over time are then updated, and the time step advances for the next iteration. This is what the output of the program looks like. Note that while delta K, delta U grav, and delta U spring are all oscillating, delta E remains constant at 0. Furthermore, the x position over time and y position over time between the experiment and the model are fairly similar, but the experimental values tended to be lower in magnitude than the model values. This difference can be attributed to several sources of error, including camera lens distortion, motion blur from the oscillating mass making its edges unclear, human error from manually placing the tracking points, slight loss in total energy due to friction and heat, and any motion in the z-axis. For the computational model, possible sources of error include rounding values derived from tracking. Now for the model system, the energy principle was satisfied, as the change in total energy, delta E, stayed at 0 since no external work was done in the mass spring Earth system. Using the x and y position data, it is possible to estimate the period of oscillation of the block. However, using the x position data yields a slightly different period than the y values, as the x position over time and the y position over time do not oscillate together. This can be seen in the annotated graphs to the right. Between 1 and 2 seconds, the x position is at a peak and the y position is at a trough, but between 8 and 9 seconds, both the x and y positions are at a trough.